Hello, welcome students. Today we are in our fourth part of the chapter Electrochemistry, and in this part I will discuss the topic variation of conductivity and molar conductivity with concentration. First is variation of conductivity with concentration. Conductivity always decreases with decrease in concentration, both for weak and strong electrolyte. It means as the concentration of this particular solution gets decreases, the conductivity also gets decreases. It is for both weak electrolyte as well as for strong electrolytes. The conductivity of a solution at any given concentration is the conductance of 1 unit volume of the solution capped between two platinum electrodes with unit area of cross section and at a distance of unit length. As we have discussed in our previous video, the definition of conductivity is the conductance of the unit volume of a solution capped between two platinum electrodes with unit area of cross section and at a distance of unit length. So from here the conductivity is the conductance of 1 centimeter cube of the solution or 1 millimeter of the solution. So conductivity in general, conductivity is denoted by K kappa. Conductivity means conductivity equal to, it will be equal the conductance of the solution per unit volume. According to this definition, conductivity will be the conductance of 1 centimeter cube of solution or 1 millimeter cube of solution. Means conductivity is the conductance of a solution per unit of volume. So it means as we increase the volume of the solution, it means decrease of concentration means suppose we have a container or a beaker in which the electrolyte is present. This is the electrolyte. And the amount of electrolyte is the volume of that particular solution which is present. Suppose it is 1 ml. Initially the amount is 1 ml. And this is the concentrated solution of electrolyte. And as we decrease its concentration, so we will add water in it. For decreasing the concentration, we will add water. And as we add water to this solution, the dilution will increase. Concentration gets decreased but the dilution will increase, and suppose we add 1 ml of the water into this 1 ml of the solution, the whole now as we add the water, then the whole volume of that particular solution will get equal to 2 ml. It means on decreasing the concentration or on increasing the dilution of an electrolytic solution, the volume will get increases. And as the volume gets increases, the conductivity of that electrolytic solution, either weak or strong electrolyte, will get decreases, because conductivity is the conductance of 1 centimeter cube or 1 unit volume of the solution. It means it is the conductance per unit volume of the solution. As conductivity increases, as volume increases, conductivity will get decreases. So upon diluting the solution, the concentration of ions per centimeter cube of the solution decreases. Therefore conductivity will get decreases. Next is variation of molar conductivity with concentration. Molar conductivity of a solution at a given concentration is the conductance of the volume V of solution containing 1 mole of electrolyte capped between two electrodes with area of cross section A and distance of unit length. Therefore, from this the molar conductivity lambda m will be equal to conductivity into volume of that particular solution or volume of that electrolyte in which 1 mole of the electrolyte is kept. From this, molar conductivity increases on increasing dilution. This is due to the fact that it is the product of conductivity K and volume V. of the solution containing 1 mole of the electrolyte. And it is found that dilution of volume of ions, on dilution volume of ions increases, which is more than the decrease in conductivity. As we have discussed in conductivity, that suppose we have a container in which an electrolytic solution is present, and the amount of this electrolytic solution is suppose 1 ml. And on dilution, as we add water to that electrolyte solution, volume of the solution will get increases. Suppose we add 1 ml of water to this concentrated electrolyte. Suppose we add 1 ml of water. What will that final volume of that solution? On adding water, the volume will get increases, and the final volume will comes to be 2 ml. And as volume increases, the conductivity will get decreases, but the molar conductivity is always increases on increasing the dilution, because here the volume will get increases. And on dilution, volume of ions increases, which is more than the decrease in the conductivity. So as a result, molar conductivity increases with increase in dilution. Now here in this, we will discuss the variation of molar conductivity with concentration for strong electrolyte and for weak electrolytes. Conductivity for strong electrolyte and weak electrolyte is same. Conductivity will get decreases on increasing the dilution. It is common for strong electrolyte as well as for weak electrolyte. But there is a variation of in molar conductivity for strong electrolyte and weak electrolyte. Let's start with the variation of molar conductivity with concentration of for strong electrolyte. For strong electrolyte, the molar conductivity M increases slowly with dilution. It increases slowly with dilution. When concentration approaches 0, the molar conductivity is known as limiting molar conductivity, and it is represented by the symbol delta M naught, limiting value of molar conductivity. And at this time, the value of molar conductivity is equal to the limiting molar conductivity when concentration approaches 0. When concentration approaches 0, it means dilution is infinite. It means we are adding water to the concentrated electrolytic solution, and the concentration of that electrolytic solution approaches to 0. Whereas at the same time, the dilution will get infinite. Because dilution and concentration are opposite to each other. As concentration approaches 0, dilution will get infinite. Variation of molar conductivity with concentration may be given by the expression lambda m equal to lambda m naught, limiting molar conductivity, minus A into concentration to the power half, square root of concentration, where A is constant. This equation is called Debye-Huckel-Onsager equation. Now from Debye-Huckel-Onsager equation, the graph is plotted between molar conductivity and square root of the concentration versus square root of the concentration for strong electrolyte. As we plotted the graph of strong electrolyte KCl and SCl, it has been noticed that variation of molar conductivity with concentration is small. We can see from this graph also the variation of molar conductivity with concentration is small, so that the plots can be extrapolated to 0 concentration. Since the variation is very small, molar conductivity increases slowly on dilution. It means it with respect to concentration, it will get decreases slowly. So there is a small variation with the concentration, so we have to extrapolate the graph to 0 concentration. As we move to 0 left hand side of the concentration axis, so we will approach to 0 concentration site. Here it will be a 0 concentration site. The intercept gives the limiting value of molar conductivity. As we approaches to 0 concentration site towards this left hand side, we have to extrapolate these graphs. And after extrapolation of graph, we will get a point here. We will get this point, and this point is known as limiting molar conductivity. Molar conductivity at infinite dilution. When we are approaching our concentration to zero, then we get a molar conductivity, and that molar conductivity is known as molar conductivity at infinite dilution, when our dilution becomes infinite. So at that time, the intercept of this graph is known as limiting molar conductivity, that is del m naught, and the slope for this graph will be equal to minus of a, which comes from Debye-Huckel-Onsager equation. The value of a for a given solvent and temperature depends on the type of electrolyte, that is, the changes on the cation and anion produces on the dissociation of the electrolyte in the solution. For NaCl, the value of A is charge of cation is 1 and charge of anion for NaCl is also 1. So the value of A is 1 by 1. So this is the graph or the variation of strong electrolyte, molar conductivity of strong electrolyte with concentration, in which we have to extraplot the graph to achieve the infinite dilution for strong electrolyte. And as we extrapolated the graph after approaching the concentration towards zero, and we get at infinite dilution a value of molar conductivity that is known as limiting molar conductivity or the molar conductivity at infinite dilution. Similarly, next is the variation of molar conductivity with concentration for weak electrolytes. Weak electrolytes like acetic acid have lower degree of dissociation. We know that the weak electrolytes have low degree of dissociation. Value of alpha for weak electrolyte is low at higher concentrations, and hence for such electrolytes the change in molar conductivity with dilution is due to increase in degree of dissociation, and consequently the number of ions in total volume of the solution that contains 1 mole of electrolyte. In such cases, the molar conductivity increases steeply on dilution, especially near lower concentrations. Therefore, the value of infinite molar conductivity cannot be obtained by extrapolation of molar conductivity to zero concentration. For weak electrolyte, we cannot extrapolate the graph. Why? Because the value of molar conductivity with concentration decreases steeply with concentration. This can be shown with this graph also. The value of molar conductivity decreases with concentration, and here it is decreases in a very slow manner. It is decreasing steeply with concentration or increases steeply with dilution. So as it decreases steeply with concentration, so we cannot extrapolate the graph to attain the limiting molar conductivity at infinite dilution. We can't reach the infinite point for weak electrolyte here, as the molar conductivity is steeply decreasing with the concentration. So therefore, to overcome this, the molar conductivity at infinite dilution for weak electrolytes is obtained by using Kohlrausch law of independent migration of ions. Now, what is Kohlrausch law? This law states that the molar conductivity at infinite dilution for a given salt can be expressed as the sum of the individual contributions of the ions of the electrolyte. Individual contribution means contribution of cation and contribution of anion in the solution. So from this definition, the molar conductivity at infinite dilution for weak electrolyte will be equal to individual molar conductivity of cation at infinite dilution plus individual molar conductivity of anion at infinite dilution, lambda naught. Here V plus and V minus are the number of cations and anions per formula unit of electrolyte. Lambda naught plus and lambda naught minus are molar ionic conductance at infinite dilution. For example, suppose we have NaCl. So according to Kohlrausch law, the molar conductivity at infinite dilution for NaCl can be written as molar conductivity of sodium cation, molar conductivity of cation, that is sodium ion, lambda naught Na positive plus lambda naught chloride ion Cl negative. Similarly for MgCl2, magnesium chloride, molar conductivity of magnesium chloride is lambda naught magnesium ion Mg2 positive plus 2 into lambda naught Cl negative, since MgCl2 when it dissociated in the solution, it gets Mg2 positive ion plus 2 of chloride ion. So here V minus is there, which is the number of anion per formula unit of electrolyte, that is 2 for chloride ion. Applications are also there for Kohlrausch law. First application is the calculation of molar conductance at infinite dilution for weak electrolytes. This law is used to calculate the molar conductance at infinite dilution for weak electrolytes. Let us calculate the limiting molar conductivity for weak electrolyte acetic acid CH3COH. So according to Kohlrausch law, molar conductivity of acetic acid will be equal to molar conductivity of acetate ion, individual ions, sum of molar conductivities of at infinite dilution of individual ions. So molar conductivity of acetate ion at infinite dilution plus molar conductivity of hydrogen ion at infinite dilution. This equation can be obtained by the knowledge of molar conductivity at infinite dilution for some strong electrolyte. This equation can only be obtained if we have the knowledge of molar conductivity of strong electrolyte. So to obtain this particular equation, we have to combine some equations of strong electrolyte. So from combining some molar conductivities of strong electrolyte, we can get the molar conductivity of a weak electrolyte. So this is the application of Kohlrausch law. For example, some strong electrolytes are HCl, NaCl and acetate ion CH3CONa. So from Kohlrausch law, molar conductivity of acetate ion sodium acetate, molar conductivity of sodium acetate will be equal to molar conductivity at infinite dilution for acetate ion plus molar conductivity of Na positive at infinite dilution. Similarly for HCl also, and same for NaCl. Now as we combine these three equations, these all are strong electrolytes, and as we combine these strong electrolytes, we can find the value of molar conductivity at infinite dilution, that is lambda m naught for a weak electrolyte. How it is possible? Let's see. On combining the equation, as we add, suppose this is equation 1, this is 2 and this is 3. As we add equation 1 and 2, as we add equation 1 and 2, we will get this. On addition of equation 1 and 2, we will get this line. And as we minus equation 3 from the addition of 1 and 2, we will get this. Why we do so? We did so because here two ions are common in this equations. The common ions are lambda naught of Na positive. Here it is lambda naught of Na positive, lambda naught of chloride ion and lambda naught of chloride ion. As we combine the equation, the common ion will get cancelled out. Now as after rearranging the equation, we will get it as on adding two equation and subtracting one equation from those two equations, we will get that lambda naught for acetic acid will comes to be lambda naught of sodium acetate CH3CONa plus lambda naught of HCl minus lambda naught of NaCl. So this is the way of calculating the molar conductance of infinite dilution for weak electrolytes using the molar conductance of strong electrolytes. Second application is calculation of degree of dissociation of weak electrolytes. Molar conductivity of weak electrolytes depend upon its degree of dissociation and it is denoted by alpha. Higher the degree of dissociation, larger is the molar conductivity. Then degree of dissociation at any concentration is alpha equal to lambda C upon lambda naught M, where lambda C is the molar conductivity of solution at any concentration and lambda naught M is the molar conductivity of solution at infinite dilution. Similarly, calculation of dissociation constant of weak electrolytes. Since we know that the dissociation constant K of weak electrolyte can be written as K will be equal to C alpha square upon 1 minus alpha. As you have studied in 11th class that the dissociation constant for weak electrolyte is equal to C alpha square upon 1 minus alpha, where C is the concentration and alpha is the degree of dissociation. Suppose I have weak electrolyte as CS3COH, acetic acid. It dissociates into its ion acetate ion and H positive. Initially, before dissociation, the concentration of acetic acid is C and the concentration of its ion is 0 before dissociation. After dissociation, as the acetic acid gets dissociated, so the concentration will get decreased and it will reduce by C alpha, C minus C alpha. Now the concentration of its ion becomes C alpha and C alpha. So for this, at equilibrium, the dissociation constant will comes to be C alpha into C alpha, concentration of product divided by concentration of reactant terms. This is the equilibrium constant. Reactant term is C minus C alpha. So on rearranging this equation, we will get dissociation constant K as C square alpha square upon C. We can take C as common in the denominator, so 1 minus alpha. So from here we will get the value of K, and that is C alpha square minus divided by 1 minus alpha. So from the Kohlrausch law we can calculate the value of dissociation constant for weak electrolyte as well. See the question related to molar conductivity at infinite dilution. Given is the molar conductivity at infinite dilution of aluminium sulfate Al2SO3 is 858 Simon centimeter square mole inverse. We have to calculate the molar conductivity of aluminium ion, and given is molar conductivity at infinite dilution of sulfate ion is 160 Simon centimeter square mole inverse. So here is the solution. According to Kohlrausch law, molar conductivity at infinite dilution for aluminium sulfate will comes to be this: 2 into molar conductivity of aluminium ion plus 3 into molar conductivity of sulfate ion. Why? Because as you dissociate this, so you will get 2 Al3 positive ion in the solution plus 3 sulfate ion in the solution. So from this, the value of equation of Kohlrausch law comes to be this. Now given the molar conductivity at infinite dilution is given, and similarly it is for sulfate ion is also given. Now on putting the values in the equation, we will get the value of molar conductivity of aluminium ion, and the molar conductivity of aluminium ion comes to be 189 Simon centimeter square mole inverse. Next question is the molar conductivity of 0.025 mole per liter methanoic acid is 46.1 Simon centimeter square mole inverse. Calculate its degree of dissociation and dissociation constant. Here we have to calculate the value of alpha, degree of dissociation, and dissociation constant K, and some values are given here. So let's see the solution part. Given is molar conductivity at any concentration is given, that is 46.1 Simon centimeter square mole inverse, and concentration is given, which is 0.025 mole per liter. So according to Kohlrausch law, molar conductivity of methanoic acid will be equal to this: summation of molar conductivity of its individual ions at infinite dilution, and from here the values are given. Values of molar conductivity of individual ions are given, and on putting all this value we will get the value of molar conductivity of infinite dilution for methanoic acid, and it comes to be 404.2 Siemens centimeter square mole inverse. Since we know that degree of dissociation is dissociation alpha equal to molar conductivity at any dilution divided by molar conductivity at infinite dilution, on putting the values we will get the value of alpha, that is degree of dissociation 0.114, and we know that the value of dissociation constant is K is equal to C alpha square upon 1 minus alpha. Now on putting the value of concentration and degree of dissociation, we will get the value of dissociation constant K here. Now on putting these value, we will get the value of K as 3.67 into 10 to the power minus 4. So that's all for today, and we have completed the application of Kohlrausch law as well, in which we can from this we can find the molar conductivity of at infinite dilution for weak electrolytes, degree of dissociation for weak electrolytes, and dissociation constant for weak electrolyte. From this we have solved this example also. Now I have some questions for you. Go through the question and solve them. These are some questions for you. Solve these questions. So that's all for today. Thank you.